Hey, welcome to another Python meetup. This one is for September. Is that the month we're in? September.
Yeah.
All right, thank you. Thank you to Organic Box for sponsoring this meetup. If you're interested in sponsoring or your company's interested in sponsoring, please reach out to one of the organizing committee members. Thank you to Startup Edmonton for this space. They provide this beautiful space for us to meet, so that's great. Thank you. We have a Pac-Man rule, so when you're standing in a group and you're talking, just leave one space open for someone else to join in on the conversation. So we just like to do that, make everyone feel like they're welcome. The talks today is Permutations and Combinations with Itertools by Abram. If you are interested in giving a talk, please come see me, because we are looking for people to give talks. If you are on the fence and you're like, well, I don't really know, I don't have anything to talk about, guarantee you have more than I do to talk about. Nobody wants to listen to me talk, so please, please, please come and find me after the meetup or whenever you're free and just say, hey, Andrew, I'd like to give a talk. If you're a beginner, then you are perfect to give a talk, because there's lots of beginners here, and I don't know what they want to be talked to about. So if you're a beginner, then you know that. So that's great. There's 2 events coming up, the DjangoCon USA and PyCon Canada 2019. Yeah, a few of us are going. I'm not going to the PyCon Canada. So if you are going, let someone in Slack know, and then they'll be like, hey, you want to go hang out for stuff afterwards or whatever, right? So cons are really great because not of the presentations there, but for networking and meeting people, right? So hanging out after them. News, Django's security release. Yeah. Jobs, Levin is still looking. They do home automation, basically smart light switches, but without wires. So they run off of a coin cell battery, turn on and off a light. They're looking to do more stuff like that that's interesting, maybe like a bathroom fan or something like that. They're working on apps and stuff. If you want more information, come speak to me. I know there are programmers there, and it's a really great job. So, if you have a job and you like it posted here, let me know. Yeah, there's a few articles. Optimizing Postgres with full text search. So that's like if you were to do this article contains the word Andrew, which is an awesome word, then find all the articles and return them. So you can optimize that in Django because Django wants to do it for every database, but you can optimize it specifically for Postgres. Dependency handling in Python. 4 use cases for when to use Celery in Flask, which is Celery is just like a framework for kicking tasks off to a background worker. So it's really good. A Python chat tutorial with Django and React. So that's a good tutorial. I disagree with it. I don't think Python's very good for chat or for any real-time applications, because everybody knows Python multi-threaded sucks. They are getting better, but not very quickly. If you wanted to do Python and real-time chat, please use Django channels or Tornado, Twisted, maybe Flask. But yeah, or a different language. Different languages are great for that. Go. Yeah, just anything not Python. Python for natural language processing, so working with Facebook fast text library. So just to take a document and then say, hey, how does this document relate to these words, right? And then article about lists and tuples. So the difference between a list and a tuple is a tuple cannot be edited. So you don't have to read that, you know that now. Friendly traceback, so you know how when something happens in Python and something errors out, you always get that traceback and you don't know what actually happened. Well, this guy wrote a great library that just makes it a more friendly error message. And you might remember from the last meetup The Python tip was to use PDB, which is the Python built-in debugger. So if any of you are familiar with GDB, PDB is just better. It's more user-friendly. And this, someone wrote a remote PDB, which means that it'll run on a web server, and then you can remotely connect to it and remotely debug something, which is fantastic. Python tip. So the tip is to join the Edmonton Python Meet Slack, ask questions, and build your network. So come talk to people and get more friendly, get to know people. That's the tip. We also have another tip. If you're using lists in a function as the parameters and you have them as default, just don't. Instead, just use none and then say if the color is none, then assign it a new list. The reason being is the top will not do what you want, and it'll actually output, so it'll output orange, red, well, black, orange, red, green, and then it'll say, anybody help me? No? Black, and then black, black, and then black, black, black. Yeah. Pretty sure that's what it does. If not, we have it on videotape, so can't really complain. The next meetup is October 14th. Is Mandy here? Mandy, can you come and talk? Or you
hello, everyone. My name is Mandy. I am part of YEG Women in Tech. We are trying to start a new thing. We want to have a bunch of events that are friendly to women in technology and allies. Our first event is a brunch on September 21st, sponsored by Dotdash. We have tickets on Eventbrite. The link has been sent all over the Dev Edmonton Slack. If you're part of that Slack and you don't know where it is, I can point you to it. Just come find me later. Or you can go to bit.ly. Actually, I'm not going to read a URL to you. It's just going to go poorly. But the link is all over Slack. Our end goal is to have a conference as well, probably sometime in February, March, something like Develop Ed for those of you who are here. So if you want to be either involved or you want to go to our events, message me on the Dev Edmonton Slack. Just look for Mandy Meindersma. Good luck spelling that, but I think I'm the only Mandy, so okay, thank you.
Thank you. So, Abram, can I have a warm welcome for our first presenter? Abram.
All right, so if you want to follow along with this presentation, go to my GitHub. I'm Abram Hindle on GitHub, and go to /fox-goose-beans. I know it should have been called something like combinations and permutations, but whatever. Then click on this Python notebook, and it will render up on GitHub for you. All right, today I'm going to talk to you about Cartesian products, permutations, and combinations, and how to do them in Python. So, first of all, we'll just do a little bit of review. Cartesian products are pairs of all elements or two or more sequences. So if I give you the sequence A and B, and I give you the sequence 1 and 2, the pairs of those sequences will be A1, A2, B1, B2. So that would be the product. Permutations are the all reorderings of subsequence of a sequence. So a permutation of ABC will be BAC, CBA, and a couple others I forget. Combinations will be unique subsets of a sequence. So if I give you ABC and I want all combos of two elements of that sequence, you'll get AB, BC, AC. Okay? So that's where we're going to start. We're going to talk about how we get these things in Python. So first off, we're going to talk about permutations. So given a sequence of n unique objects like dog, cat, A, B, 1, 2, true, false, a permutation is a sequence of n of those objects or a subsequence of at least n of those objects or whatever. That one's wrong. Permutations of size 2 of A and B are AB and BA. Okay? So permutations are order dependent. Okay? So we have a sequence and we want things out of the sequence in order, and those are the only two permutations we're going to get of AB and BA. Will we get AA or BB? No, because we're going to use all the objects once. Okay, so a permutation of size 3 for A, B, and C are all the permutations start with A, all the ones that start with B, and all the ones that start with C. So we got ABC, ACB, BAC, BCA, CAB, CBA. Okay? So these are pretty interesting because they're all the ways you can order things. Given n things, how many different ways can you order them? So that's pretty interesting. We can also get smaller subset permutations from the original permutation. So if we say we have A, B, and C, but I want all size 2 permutations, I get AB, AC, BA, BC, CA, CB. Okay? Never is C repeated twice. Never is A repeated twice. They're all in there. They're all done once. Okay? So these are pretty neat. We use them all over the place. You deal with them all the time in terms of ordering, when you pull things out of a bag, anything along those lines. So the problem is that there's many permutations. So given n objects, there are n factorial unique permutations of those objects. N factorial is n times n minus 1 times n minus 2 times n minus 3 times ... times 2 times 1. So it's all the numbers from 1 to n multiplied together. It's the product of all those numbers. So that number gets really big. Just be aware of that. So if you want all permutations of something, if you ask for all permutations of 100 things, that's a lot of numbers, you know. Like, okay, like 100 is like almost 2 to the 7, right? So I'm going to, right? So go 50 times 7, right? So that's 350, right? So that's basically to the power of 350, like 50 to the power of 350 or 100 to the power of 350. I'm kind of guessing there, but that's a really big number. We can't represent it with floating point numbers though, so it's not super big. That's cool. All right, so just be aware that there's a lot of permutations, right? We can have less permutations if we have a small k, but in general, there's a lot of permutations for any given sequence. So this is a problem because we have limited memory, right? So we might run out of memory if we were, say, to make all permutations in memory. All right, so first off, you want one permutation. So the module random is super awesome. Comes with lots of random utilities for random numbers, picking and choosing, all that kinds of stuff. But random shuffle is your friend. Random shuffle will take a list or a tuple or an iterable or whatever, and it will reorder that list uniformly randomly, which means that in every location, the probability of something being there is just as likely as it being in another location. But it's a permutation, which means that if you had A, B, C, it's not going to output a random list of AAA, it's going to output a permutation of A, B, C. Okay? So if you have any questions, please ask. This talk is aimed at newbies, but also people who have computer science degrees. So it's all over the map, and you might need a clarification, okay? So I'm perfectly fine with questions, and frankly, they entertain me more than me talking entertains me. So if you have questions, I'd love to hear them. Okay. How do we shuffle? How do we get one permutation? Well, we can look at the Fisher-Yates shuffle, which is not a dance, but you could probably make a dance out of it, like maybe a polka. Okay, so we take L, that's your iterable, and we get the length of L. If the length of L is greater than 1, then we do this. Otherwise, we just return L. So what do? We go from, is there a bug there? That's a good question. We go from 0 to n minus 2. I think it should be n minus 1. Anyways, we go from that in that range. We choose a j, and that j is a random integer. And that j is greater than or equal to Ri, and it's less than n. Okay? So we're choosing a random spot to jump to. Okay? And the range becomes smaller as we go down the list. So we're going from, say, if we have 3 elements, we're going from 0, 1, 2. Our j will be one more than that. Will be equal to one more of that. Then we do this Pythonic swap. So once we choose the j, we say swap what we're at now with the random choice that we've got. What this says is for ji, so j of l and I of l, put j of l into I and put L of I into L of j. Okay, so that's a swap in one line. You might not have seen this before, but it's equivalent to going temp equals Lj, Lj equals Li, and then Li equals temp. So you could do it in 3 lines. Python does this tuple thing, so you can do it in 1 line. It's kind of nice. So any questions about this? Okay, so this shuffles your values, okay? And so what we can do is we can run it a couple of times. We can shuffle numbers, and we can go take a look. So here's the Fisher-Yates shuffle, and it took the range 0 to 9, and it shuffled them. They're in random order. At least they look random enough to me. So this is a permutation. 0 only occurs once in every one of the lines. Of course, you don't need to use Fisher-Yates shuffle, which I just taught you, which is proven to work really well and runs in linear time. If you have n objects, it goes over every object once, so that's cool. You can just call random.shuffle. You don't need Fisher-Yates shuffle. Do they use Fisher-Yates shuffle? Probably. Doesn't really matter. You're relying on a black box to do the work for you, and it's trustable. Okay? So random.shuffle, your friend will give you 1 permutation. That's cool. So if I want all the permutations, I run this, I don't know, n factorial log n factorial times, and I'll get all the permutations. Oh, you didn't want that, did you? No. You want all the permutations without doing it a stupid amount of times. Okay, so how do we get all the permutations? Well, this is way more fun. But you got to realize there's a lot of permutations. So here I'm getting the factorial. Math has a little factorial function, integrate, of n and half of n. So I'm saying I want, if I have, say, 100 elements and I want 50, I want permutations of 50 of the elements, how big is that going to be? So if we scroll down just a little bit, oh, I forgot, this is the, yeah. All right, scroll down, scroll down. Here we go. How many permutations are there of 100 elements? I don't know, that's a lot. That's a big number. How many permutations are there of 50 of 100 elements? Okay, there's less. It looks like less to me. 3 times 10 to the power of 93. So 93 zeros. Okay, too big, right? Really big. How many permutations are there of 10 elements of 100 elements? Okay, 2 to the 19. Now we're dealing with almost 64-bit numbers there. That's cool. That's mainly addressable. So if each of those permutations takes only 8 bytes to store, right? Which it doesn't. We're talking Python here. How much memory? About 500, I think it's exabytes, or is it etabytes? I think it's exa. 1 exabyte is 1,000 petabytes. 1 petabyte is 1,000 terabytes. And 1 terabyte is about $300 SSD, right? In memory, it's about 10K for the box and everything. Okay, so that's too big. And also, that's too high of a number to ask Python to do. You shouldn't use Python for that. Okay, so, okay, we know that there's a lot of permutations. We know they blow out of control really quickly. I still want them all. Okay, that's a legitimate question. How do we calculate the permutations, and how do we do it memory efficiently? Because it's not going to be CPU efficient no matter what we do, because there's n factorial of them. So that's out the window, but let's do it with less memory. So Donald Knuth came along, and he didn't come up with the algorithms, but he did compile them in his book, The Art of Computer Programming. So volume 4 has chapters on permutations and combinations, and they have lots of neat descriptions of alternative algorithms and different ways of thinking about it. But one of Knuth's algorithms that he suggests, it keeps a minimal state, and it iterates through all the permutations by only keeping 2 lists of numbers. One is like a list of the indices, and the other is a list of swaps. And so for given n elements, you'll have a list of indices representing those elements, and then you'll have another list of swaps. The swaps are just the last spot it was swapped with. Okay? So that means in n memory, aka if you had 10 objects, you only needed 20 memory to do this permutation, do all the permutations. So that's pretty handy. We don't need n factorial memory, so that's great. So how do we go through them? It's actually a really clever way of swapping. So imagine we have A, B, C. Let's go to the back and let's swap B and C. Now we have A, C, B. Okay? If we swap them again, we get the same value again, right? So what we do is we have a counter that says, hey, you already swapped those. Don't swap them again. So we move on now to that A column. So now we swap A and B. So we get BAC. And then we can swap again and move the A around, and we can get our BCA, stuff like that. So really, it's about keeping track of swaps. And you can do this without a lot of memory. So for small numbers, you can compute this. For large numbers, like say permutations of 100, I wouldn't bother. We already went through that. That's a lot of permutations. So the Python code's pretty good. If I can just scroll, I will. Let's do the Pythonic stuff. Okay, so this is kind of an implementation of the algorithm. We take a copy of what you're iterating over, we get its length, we deal with if you want subpermutations. If you ask for a subpermutation that's bigger than what we currently have, instead of asserting, we return, which is not nice, but whatever. We make a list of indices from 0 to n-1 of your pool of iterables, and then we make a cycle list. And the cycle list goes from n to n-r, which could be n. So go from n to 0 in most cases, and it decreases. So it goes n, n-1, and so forth. So that's our cycle list. Then we have this pleasant infinite loop done in Pythonic style, because we want an infinite loop. And I have this little debugging thing here, because this algorithm's confusing. And then we go from I reversed of range r, which is n, which is the length. So that means we're going in reverse order, okay? So we're now going down instead of up. If you read Knuth's books, he loves while loops that decrement. He just does. It works pretty well for him, so he keeps doing it. Now, you reverse decrement, and then you take your cycles array, and you subtract 1 on the current thing that you're at. That's basically keeping track that you're just evaluating that position, that swap, already. Then, if you've got cycles equals 1, you're actually all the way at the end of the list pretty much, or you've already reached the end of the list, and you just do these swaps. Otherwise, most cases, so this is what mostly will run, okay? This will run more of the time. We'll go j equals cycles I, just to keep track of it, and then we'll swap indices I and indices j. Oftentimes, this swap will be the same thing, okay? Just watch out for that. Then we yield. What are we yielding? We're taking your original objects and we're remapping them using the indices. So instead of moving your objects around, we're really just moving some indices around. So if our indices end up looking like 0, 1, 2, 3, we are going to return 0, 1, 2, 3 of your objects. So if you had A, B, C, D, we're going to go A, B, C, D. But if it was 3, 2, 1, 0, it would be D, C, B, A. Okay? So it keeps track of that. Now, this is a lot to think about. This is a little confusing, and you're getting slammed with a pretty complicated algorithm that's basically doing repeated swaps over and over again, and it's pretty hard to deal with it without some debugging help. So we've got the printout. So we ran it, and it yielded the first result, A, B, C, D. So it output the first result. That's what yield does. It's like an intermediate return. Does everyone here know what yield does in Python? I can explain it if you don't understand. Okay, who wants to know what yield does? Okay, the majority of the class. Okay. All right, so if I make a function, and inside of the function I call yield, what it does is it actually returns that value as an iterable value. Okay, so you could imagine that I have the function def f l, so it takes in the list L, and then I go for I in L, yield I. What that's going to do is it's going to return every element in a iterable. So what I can do is I can go for object in f of L, print object, and it will iterate through all those objects. But what if I want to do something like, I want to return double the objects? Well, I could go yield I, and it would return it twice. So I can return lots of objects with the yield. Okay? So yield is a flow control mechanism that's kind of like a thread that picks itself up every single time you call it through an iterable interface like a for loop. Okay? So the APIs for your iterables are usually you can call next on it, and it will give you the next object. And that's kind of how it works. So we're basically using it here in permutations. Every permutation we get from A, B, C, D, we're printing that permutation, okay? So it's yielding that permutation. It's yielding from the pool, based on those indices, that permutation. Is it returning it? Did we call return? No, it's actually dealing with that yield coroutine iterable API. Okay, so what Python's doing is permutations is running, and then when it yields, like right here, it stops. It keeps the state of the function, so that's recorded, and it stops and it returns that value, okay, via yield, via that iterable interface, okay? So it allows us to get values from inside the function as the function runs without using threads. If I was using a thread, what I'd probably do is instead of yield, I'd say message my queue or add an element to the queue, right? And then they could be running at the same time, whatever, okay? This means this is running until we yield. Once we yield, we stop, and the next time you ask it for something else, it carries on, breaks here, repeats the infinite loop, okay? Any questions about yield? Because it is complicated. All right. So let's go back to here. Yields this, prints this. Okay, so the first one is yielded automatically because we just print the first thing by default. Okay, now we're going to look at our cycles, and we've got 4, 3, 2, 1, and we got indices 0, 1, 2, 3. Well, that makes sense. And then we mutate that, and we've done a swap, right? We've swapped the 2 and the 3, right? And if you look, what thing did we decrement? We decremented this because we swapped on the second one. So we swapped C and D, okay? Then the next one, right, that we yield is ACBD. And you can see that we've decremented one of our cycles here, the later cycle, and thus we've swapped 1 and we swapped 1 and 2. Or no, we swapped out to there, yes. So we swapped this position with that position, okay? So do you see the difference between these two ones? This is 1, 3, 2, and this is 2. Oh, it's swapped twice, yeah. Okay? Then the next one, ACDB, our cycles now read 4, 2, 1, 1, and our indices are now 0, 2, 3, 1, so it did swaps there. And then it swaps again over here, all these 3, and we get that. And we go forth, and it goes on for a little bit until it finally stops where our cycle counters are all 1, 1, 1. We've now flipped through all the cycles enough times, and our indices are fully reversed because our indices started at 0, 1, 2, 3, okay? And in the process, we yielded every permutation. And how much memory did we use? An array of indices, an array of cycles, and of course, well, we made a new list every single time we yielded, but let's not talk about that. Okay, that's cool. All right, that's kind of complicated. Do you want to rewrite that? No. Itertools is your friend. Itertools comes with this out of the box. Itertools.permutations. Nice. These are super useful. It's super useful to iterate. So, as you can see, with Itertools, we get the same output. it's yielding, and the API is the same. It's this kind of yield iteration API. That's cool. What if you just want a list of them all? Does anyone know how I get a list of all the permutations immediately? How do I get a list of all the permutations? Does anyone know how to force an iterable into a list? Rapid in list, yeah. So I could just go list, open paren, close paren, bada bing, we got ourselves a list. Oh, your permutations are too big, you ran out of memory. So watch out with the size that you put in there, because it'll just explode on you. Combinatorial explosion. All right, so we get all the permutations. That's cool. Also, Itertools lets us do permutations of a size. This was everything, but what if I just want 2? So I got AB, AC, AD, BA, BC, BD, so forth. Lots smaller. Kind of cool. All right? So one last example before we go off and eat, before we start combinations, is the Scrabble example. I play Scrabble with my mom a lot, and my aunt, who is vicious and will challenge your words. But sometimes they don't know that I'm on my computer. All right. So in the game of Scrabble, you get a series of letters, and you can form a word, right? And the words really are permutations of the letter tiles that you get. So given letters, what words can I form? So to do this, I want to get some words, want to get some input letters, and then for permutations of size 2 to n, this is supposed to be below, are any of these actually words? So this is actually very easy with Itertools. So what I'll do is I'll go and read a file. I'll open a file here, and then for every line in the file, I'll strip the line and remove the new line. I have a list of English words. They're all uppercase, lowercase, and they're new line separated. So it's just a list, alphabetical order, from A to whatever the last Z word is, probably not zebra, but it's in there. Then I take an input word, such as the name of the game, Scrabble. Then, for I in range 2 to the length of the word, I'll then get every permutation of the word of that size, and then I'll make a string out of it. And then if that word is in my list of original English words, because remember, words like BBLE are not English words, right? So I'm checking to see if they're in my dictionary, just using in. I'll print the word. So what are valid Scrabble words? Maybe. Don't trust me on this. The Scrabble has an official dictionary. You should get a copy of that one. So it's saying SB is important, BA is important, B, I know that's an English word, but I have played BA and AC before, so it has worked, at least with my aunt. So let's just go down this list. There's not actually a ton. We have the 3-letter words. We got the 4-letter words like seal and seer and crab. We got albs. We got Ebs and Elsa and Caesar and Babel, bears, rabble, Scrabble. Okay, I want you to see something. Do you see a problem with the output at the bottom? Does anyone see a problem? Why do we have these two things?
There's 2 B's.
Right, there's 2 B's, and the permutation function is not asking for lexicographic permutations. It doesn't care if 2B or not 2B. It's just going to do that, right? So it's basically just giving us the permutations of the indices, and it's not looking at the content. If you care about removing these in a very efficient manner, you can go read the Art of Computer Programming and implement the lexicographic algorithm, which is not that much harder. It's pretty doable. It's not super complicated. It's about the same size as that past permutation code. If you don't care, well, you just, I don't know, keep a list and make sure, since they're very close together, was your last permutation like the previous one? You can unique on these ones. To a certain extent, it might not work. You can keep a set, but then you're keeping in memory. Basically, if you really care about lexicographic permutations, you should go read the book. But out of the box, look, it does it. Boom. And it yields, and it's Pythonic. It's great. Yes?
Why did the bells go twice?
K-bells. I think because this is a duplicate B from Scrabble. So Scrabble has 2 B's in it. So this B is not this B, or this B is not that B.
Yeah, I get what you mean.
Yeah. 2 B's are not 2 B's, you know. That's kind of the problem. Yes. All right. Any other question before pizza time? All right, it is pizza time. We'll come back with combinations and products.
So that each B was a different point in memory.
Yeah, yeah. So it's like the same character, but it's, you know, in the index, it's S, C, R, A. 4 and 5 are Bs, yes. Yeah. Basically reordering of a sequence. What can you use them for? Problems where you need to iterate through everything and the order matters. Problems where you can't duplicate the objects in question. We'll discuss something that does this. And trying out combinations of filters. So if you just want to see if you know, this applied, then this applied, then this applied, if I get a certain response, permutations are pretty good for that. So if you have like 4 different filters you could apply to say even a photo, you could go through all the different ways of additively or multiplicatively applying those filters. You can also do it for optimization. You might try out all the permutations of a treatment to find the optimal order to apply. Next up is combinations. And combinations are different than permutations because they are order insensitive. They're really subsets of your original set. So because they're subsets, we don't really care about the order of the elements within the subsets, which means that if I give you the set A and B, all combinations of the set A and B are of size 2 are A and B. So it's not super useful because the ordering doesn't matter. I could give you BA, but it would be the same as AB because it's a set and it's order free. All combinations of size 3 of ABC are, well, ABC. It would also be BAC, but that's the same as ABC because it's a set, so the order doesn't matter. So with combinations, usually you select a smaller amount from the original set. So usually we go combinations of 2 from 3, right? Because combinations of 3 from 3 is the same set, but combinations of, say, 2 from 3, we get all the different combinations. So here we got AB, AC, and BC. You can rewrite these, but I'm just writing them in order such that you can see how they're done. Notice how there's no C alone, there's no double C, nothing along those lines. So it's subsets of your original set. And it's different than a permutation because it doesn't care about order, which means we can do different things and we can use different algorithms to generate these. So first and foremost, to generate a combo, what we can do, this is combo of T. All right. To generate a combo, you can consider that really we want to subselect what's there. So you could just use random.shuffle immediately. You could do random.shuffle and then you could subselect, say, the first n elements or the first k elements if you wanted that subset. That would give you a random combo. But when we're talking about combos, since we're talking about set representation, it's oftentimes useful to consider the binary representation of sets. The binary representation of sets is where I give you a binary string, like an integer, and the zeros in a column indicate the lack of that entity being in the set. So imagine I have A, B, and C. A is index 0, B is index 1, and C is index 2. Okay? So if I have a set with A, B, and C in it, I'm going to go 1, 1, 1. If I have a set with B and C in it and no A, I'm going to go 0, 1, 1. This is useful for representation because it shows us that we can use 1 bit of memory to represent if something is within a set or not. And this will be useful later. So if a combination is a binary number where each bit of 1 indicates the corresponding object is in the set, so really if we want combinations of 2 out of, say, 3 or 2 out of n, we'd really just look for binary strings with 2 1-bit set. That sounds a little confusing. So if we had a binary string of n bits and we only wanted 2 out of there and we wanted combos, we could just look for strings that had a 1 set here and 1 set over there. So the total of the count of the hot 1 bits would be 2. That's kind of cool. That actually works out pretty well. So if we want a combo of T, we really don't have to do a lot. We can basically shuffle it and get something else. So here's 3 combos from 5, and I ask for a combo of T, and I just randomly select them, and they all came out the same. I'm going to rerun it. It is possible, because I'm randomly doing it. So it's possible. All right, there we go. See? Totally random. All right. So really what I'm doing is I'm doing a shuffle, and then I make a set, and then I check to see if anything's there, and then I add it. So this is a really bad way to do it, but it's going to help you understand the following algorithm for all combinations. So I make an array A, and I've set it to false for all the items in your set, okay? And then for I to the number of elements you're looking for, so maybe 2, okay? I set those to true. Okay, so I have a list of booleans, and now if my t was 2, I've got 2 of them true, the rest are false. And I shuffle them, right? We already discussed Fisher-Yates shuffle, so we know how to do that. Then I basically make an output set, and then I go through and I look to see if one of those is there, and if it's hot, if it's true, then I add its corresponding iterable or corresponding thing to the combo, and I return the combo. Okay? That's pretty inefficient, but it's a good way to think about it. If you've got random available to you, you should have just called random.shuffle, open paren, L, close paren, and then you go a brace here, and then you go 0:T, and then it would return a combo randomly selected, which is way nicer than this code. This code is just like educational purposes only kind of stuff. Okay, so don't run this in production. It's not my fault. All right, so we can do this way. This is a nice Pythonic way, but we want to do it the hard way, and we want to use binary. So what we're going to do is we're going to use bit representation of integers, which in Python is relatively unsafe, but go for it. So the first function I need is how many 1 bits are there in number x? So given an integer x, I am going to basically see if a bit is hot. Okay? So I'll go through until I get too big, and if the bit is hot, I'll increment my count.
What does hot mean?
Oh, set to 1, sorry. Okay, so if the bit is set to 1, it's going to match, when I AND B, it's going to match, and it's going to come out as true, and then we'll increment the count, and then I'll complicated multiply B by 2. So it's just I was using bit operations, thought of bit shift. You can go multiply it by 2 if you want. It should work with the big ints. Python seems okay with that. All right, so this will return how many 1 bits are in the number. And then, because we weren't doing it the Pythonic way, I have to still get sublists out. So if I give you the integer 7, right? The integer 7, which is hot bit, hot bit, hot bit, right? I still have to be able to get those bits out such that I can subselect the array. So I want the first 3 elements of your set. So how do I do that? I use the sublist from binary indices. We do pretty well the same code here, except I'm incrementing index by 1, and I'm appending, and then I return the output. So I'm just appending, okay? So it's pretty similar, except what this one does is it takes an array, or a list, or an iterable, whatever. It takes a list, and it takes an integer, and then for every hot bit in that integer, it will pull out that value from the list. So if bit 31 is hot, it's set to 1, then it will go L of 31. It'll pull that one out. So this is useful. This means I can use an integer to represent a set. This is less useful because we're in Python. You wouldn't do this normally in Python. In Python, you just use like a list of booleans. That makes sense. Or you'd be using NumPy, and that would be even better. That might even rely on Fortran to do this actually fast. So that might be nice. Okay. So how do we get all the combinations out? We walk through all the integers. Which integers? Well, the integers 0 to 2 to the n, where n is the number of elements in your list. So if you have 3 elements in your list, it's 2 to the 3, which is 8. If you have If you have 16 elements in your list, it's going to be 65,536. You know, if it's 32 elements, it's going to iterate between 0 and 4 billion. I'm not going to work it out for you. You can do it yourself. And if it's 64, it's some huge number, somewhere like 9e10 to the 9 times 10 to the 19. Really big. Pretty big. Okay? So this is slow. This is not great. And you're thinking, but this seems really inefficient. Why are you doing this? Okay, I want you to think about the runtime of this. Combinations, n choose whatever, is still factorial. Did you know that 2 to the n has about the same big O as n factorial? Like, you can hand wave this one pretty good. It does work. So this means that this has the same runtime as outputting all the combinations, even though it's massively inefficient. Like, this is absolutely gross. I don't like it, but it does work. So we get what's happening here. We're going through all the integers, and then we're checking to see if the integers have exactly the number of bits set. So we're going 1. Does 1 have 2 bits set? No. 2. Does 2 have 2 bits set? No. 3. Does 3 have 2 bits set? Yeah, it does. Great. Once we get up to 7, it's got 3 bits set. Does it have 2 bits set? No, it's got 3 bits set. Right? Pretty neat. But this blows out of control real fast. Don't do combinations, just like don't do permutations on huge amounts of things. Cool. And how much memory do we use? Well, if this was in Python 2, a lot, but it's not Python 2, it's Python 3. So this is just an iterable, so that it's easy. Okay? Any questions about this? Okay, so just to review, we get our list in. We get the number of elements we want in the combination. We go from 0 to 2 to the n, and we see if how many 1 bits are there, and we return a sublist if the 1 bits are exactly what we wanted. So we just check how many 1 bits there are in that integer, right? And you remember your binary counting. 0, 1, or 1, 2, 3, 4, 5, 6, 7, right? That's how you count to 1,024 or 1,023 on your fingers. Yeah. So that's how we do it. And that's a naive thing, and it works just fine. You can think of a smarter one where you did it recursively, and you said, have I already selected enough to be in the combo yet? And you could search a tree of these integers, and you could stop when you have too many 1 bits set. But unfortunately, that algorithm has the same runtime as this algorithm. It just evaluates a couple less things. That's about it. So any questions about this dumb algorithm? Because this one is very naive, but it does work. As long as you have big ints. If you don't have big ints, this stuff falls apart. Okay. So does it work? Well, we did our sets. Does our 1 bits work? Is 10 got 2 hot bits? Yeah. Does 8 have 1 hot bit? Yeah. Does 7 have 3 hot bits? Yeah. So there's our unit test. We're good. Okay. Now combos of 3 from A, B, C, D, E, D, or A, B, C, D, E. And it looks like it works. That's good. So we can do this recursively in a tree where if we've now got too many hot bits, we just stop looking because there's no point going any further. You can iterate through, so you can explore space of a tree and you can basically prune, but it's the same runtime. Because you might say, oh, but it's way faster. Okay, 2 choose 100 is different than, it's going to have a similar runtime to 98 choose 100. Because your number of hot bits, not hot bits, it's going to be similar runtime because once we get into the 50-50 mark, like 50 choose 100, you're going to have an equal number of hot bits and equal number of not hot bits. It'll run faster in the small hot bits zone. It will not run faster for anything where there's a lot of hot bits. Okay? It's still n factorial time, 2 to the n time. That's still a lot of time. Okay? All right. Anyways, do you care? Not really. Itertool does combinations for you out of the box. And it's a very nice interface, and it yields and everything like that. And you get your ABCDs. Isn't that great? Thank you, Itertools. Now, why would you use combinations? Well, we could use combinations to basically see if sum of primes is primes. So the order in summation doesn't matter. X plus y plus z doesn't really matter if I go z plus y plus x, right? So if I give you 1, 2, 3, and I ask you to calculate that sum, it's the same sum as 2, 1, 3. So what's the point of reevaluating all those? So let's go check this out. So I get a bunch of primes from 2 to 50, and I want all tuples of primes less than 50 where their sum is a prime. So I ask Itertools to give me combos of 2 where their sum is prime. Okay, cool. And then what do I get? All tuples of primes with less than 50 where the sum is primes, and everything's got 2 in it. Okay, so if we carry this out longer, we're going to find out that this is a boring question when there's only combos of 2, because 2 is special, and it's special and it just sucks. But triples of 3, triples, those are more fun. So if we ask for 3, we quickly get way more things where their sum is prime. That's pretty neat. We can also count the triples of primes less than 50 where their sum is prime, and we can also count the number of times that they're not prime. And I'll just scroll down a little bit. No, there we go. So it's a lot of numbers. How many were there? How many combos? 180. How many were there not that didn't pass? 275. Well, that's kind of interesting. So if you're looking for specific numbers, especially for like some kind of dumb Facebook math quiz or something, you're just trying to go through all the solutions, just brute force it, Itertools is your friend, right? You can solve any of those dumb Facebook math quizzes with this. All right, so one example would be find a triple where the prime is sum and the digits of one of the primes is in the summation, right? So the number is prime, but it has some of the things, it shares digits with something that's summed up to it, and they were all prime anyways. It sounds kind of hard, but the code here is pretty simple. For every one of my primes is that string in the string of the sum. Cool. All right, so we go through 2 to 100, and we ask Itertools for all the combos of 3, and then we go see what happens. And it turns out that this is pretty common, and it's pretty common for a lot of reasons. A, the primes with only 1 digit are in just about everything. They're in fact in a lot of numbers. Like the number 3 is, that digit's in a lot of numbers, like in an infinite number of numbers. So many of them are prime. Anyways, if we look at this one, 4, 7, 5, 3, 97, it sums up to 197. And 97's in there. Why? Because 47 plus 53, that's 100 plus 97, bada bing. We're good. Nice. So that's really handy. So we can go through things and find all the combos. And we don't notice how it's got it nice and ordered such that each of these tuples is ordered. So we kind of understand that it's not duplicating stuff. So that's cool. So combos are really nice. Why do you use combos? Well, they're great for problems that the set matters, not the order. So things like pizza toppings. It doesn't, some people argue with me here, but it really doesn't matter when you order pizza what the order of the toppings are. Now, in terms of cooking, yes, it could matter, but I'm not going to argue with that. Secret Santa at Christmas, you want the combos of people. You don't really care about the order of the people in the combos unless you're doing like a weird graph-based Secret Santa, and you brought that on yourself. That's your own fault. Anything that has associated commutative properties, and when you got to produce subsets. Now, I use combos a lot, but it's mostly, the thing I use the most is actually Cartesian product. But before I start on that, I'll ask, does anyone have any questions about the combination algorithms that I just discussed? Okay, we're good. Let's go down to the Cartesian product. Now, Cartesian product, it's a little less set-oriented. I thought I clicked a val on that. So let me click a val on it. Cartesian products are really nice because they basically are like for loops. A lot of what you do, especially if you do nested for loops, ends up being basically a Cartesian product. So in set theory, we go A, Cartesian product B, and it produces a set that has all the tuples of A and B such that A is in A and B is in B. Okay, that's not super helpful, but if you look down here, here's the Python for it. So for given all the X objects in objects X and all the Y objects in objects Y, we yield XY tuples. Okay? Looks like I didn't push the example. So if X is true and false and Y is A and B, we're going to get true A, true B, false A, false B. So it's going to go through both the lists. Now, another common thing to do is a self-Cartesian product, where say we had the array that's had true and false in it. It's now going to produce true, 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 false, false, true, false, false. So basically all combos. That's kind of cool. Unfortunately, the Cartesian product gets really complicated when you have many sets. So for X and Y, or for Y, for Z, for U, for V, that's when it starts falling apart. And there is nice generic ways of dealing with this. So Knuth describes it as all n tuples. I have a recursive solution right here. And what it does, it's kind of like counting. So you should really think of the products like counting. Given list 1, iterate all over list 1 with the first element of list 2. Then, once you're done iterating, increment and go to that next thing. So it's like counting in a different base, right? The base is your sets. Okay, so you basically are like doing like an odometer. Kind of rolls over and then increments the next thing. It's like your first for loop is done, so you carry on with the second iteration of the second for loop. So what this does is it does it recursively. So our product calls this with an empty list of prefixes, and you give it the sets. And then in most cases, it's going to basically get the head of that list and the rest of the list. And then for every element in your first list, it's going to call itself again, right? It's going to call itself again with the prefix you passed in, this new element in the prefix, which you just pulled out, and the rest of the sets. So if this set is, say, true and false, it's going to make a prefix with a true on it and a prefix with a false on it, and it's going to give the rest of the sets to here. And then for every one of those, it's going to basically yield it. Okay, so what does it actually yield? Well, up here we can see that it yields the prefix plus the current element as a list. So it just does list concatenation. So what this would mean is if the prefix was AB true, we'd iterate through our last set. And if our last set was 1, 2, 3, it would go AB true 1, yield that, AB true 2, yield that, AB true 3, yield that. So it's just recursively kind of iterating through your lists. It's just doing a recursive product. This might seem more complicated because I've made it recursive. I apologize for that, but functional programming doesn't really, it really sticks to you sometimes. All right. So what do we get if we get the product of 3 lists? Well, we're going to basically get all the tuples that have an A with all these values and all these values. And we can do the same thing with Itertools. So let's go and let's take a look. So product of 3 lists of different types. We have ABC, 1, 2, 3, and true and false. So A, 1, 1, 2, 2, 3, 3, true, false, true, false, true, false, true, false. So it's like counting. But your number system changes on every digit. It's kind of weird. It works pretty well. So we can iterate over the product. That's kind of cool. Now, Itertools does it out of the box. So you don't really need to care how to do it, but it does do it out of the box. And it uses a nice little Pythonic thing where it does star iterables, which means that you don't need to give it a list of iterables. You just give it list, comma, list, comma, list, comma, list, and it will desplat it or whatever it's called, and it'll go through it. So if I ask it to, for a range 0 to 3, repeats of 1, it'll give me just 0, 1, 2, because there's only 1. If I ask for repeats of 2, it'll give us a self-product of 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Okay? So that was basically the range, Cartesian product with the range. Okay, so that's cool. And then the one with 3, it's all the 3 tuples of the same thing going from 0, 0, 0 to 2, 2, 2. So that's all the space. That's kind of cool. So it goes through all the points. This is good for grid searching. All right. So it can iterate over it. Now, I actually use this the most. I use this a lot. Why? Because I do what's called grid search. I have a function. It has a lot of complicated parameters. And I need to try that function on all these parameters over and over and over again. And I got to get their evaluation of those parameters. So I find the best set of parameters that produces me the biggest value. I just want the biggest one, right? So I got to search through all these combinations. So I'll do some deep learning where I'll set my batch size to 1 or 4 or 8 or 16 or 32, 64. My learning rate to 1.0, 0.1, 0.01, so forth. My activation function to a sigmoid, hyperbolic tan or a ReLU. Change even the optimizer, atom or stochastic gradient descent. Number of epochs that got fixed. And my architecture, what does the neural net look like? Does it have 2 hidden layers of 1 hidden layer? What's going on? And then I go try them out, and I go and see which combo of these parameters actually works. And that is called science. Anyways, it does work pretty well. What I typically do is I generate make files, and then I can just go make-j8 or whatever, and I can run all these on the CPU as fast as I want. Or if I got the GPU, maybe I can only run 2 at a time or something. So how do I actually run it in Python? Well, I take my thing here, and I go product times param values, and I'll just take all these lists, throw them in there, and what does it produce? Boom. Grid search, sigmoid, SGD. I'll show you how much it produces. It's quite a lot. So we got sigmoid, tanh. Our learning rate is now becoming reasonable, and tanh, more sigmoids, atom, SGD. It goes on for a while. You got to realize that the product is the size of the multiplication of all the lengths of your inputs, right? So it grows multiplicatively. It's quite big, but it's not factorial big. So that's cool. Keeps going, and then it cuts off because it was too much. So that's why I use Itertools a lot. I have to search through lots of possibilities, and I want to cover all of them. And I want to get a report about all of them. So I then basically go and produce something that's going to do all that work for me, go destroy a cluster somewhere, file in 65,000 different jobs into a batch processor kind of thing, and just ruin that cluster and get my results. And it works. It works fine. Maybe some of these are stupid and I shouldn't have searched them. I should have pruned them earlier. I should have used a better search algorithm rather than grid search. But the reviewers already complained that they wanted to see a plot with all the values. So what am I going to say to them? Okay, so this is very common. So you just have a lot of different parameters and you want to try them all. You could think of this as like running a C program and using a bunch of GCC options. Actually, you know what? I'm wrong. If you have GCC options, you probably should use all combinations. Yeah, you should. Other than like -0, -1 to 3. But you could do that. You could use combos or you could use product, and you could run time on your resulting C program and see which one actually ran the fastest or crashed the fastest if you weren't watching out. Okay? So it's good for that. Now, so let's get on to a more serious example. Fox, goose, beans. So there's this logic game. It's called Fox, Goose, Beans. Someone's probably heard of other versions of it. Basically, the farmer has to move the fox, the goose, and the bag of beans across the river. The farmer can only take one in their boat at a time, and the goose will eat those beans. So you can't leave the goose alone with the beans. And you can't leave the fox alone with the goose because, well, they don't get along, okay? But the fox has no interest in beans. We can hold one animal or object in our boat at a time, and we have to cross the river, and we cross both sides. So 2 sides of the river. I want to get the fox, the goose, the beans to the other side. So let's think this through. If I move the fox across the river the first time, the goose gets the beans. Okay, if I move the beans across the river the first time, well, yeah, the fox got the goose, I guess. Goose, yeah. So it's kind of annoying. So the farmer has to watch out because the farmer loses if the beans get eaten by the goose or the fox eats the goose, and we can only take one object across. If the farmer is on the same side as the fox and goose, he can prevent the fox from eating the goose, and he can prevent the goose from eating the beans because he has, I guess, 2 arms. So I guess the idea is it's holding back both and maybe pushing the beans out of the way with the leg. But he's got to huck one of those onto the boat. So there is an order in which he has to move these animals or things onto the boat back and forth. So what we're going to do is we're going to look at what is the minimum number of moves to win and what is the path to win. What is the operations I have to do? So first off, I model the situation. Our start state has fox, goose, beans, farmer. Our state will be represented by 2 sets, which was a bad design decision, but I stuck with it. We have a thing here to copy the state because I kind of wanted to keep it functional. It didn't quite work. We evaluate the state. Let me just see here. If the fox is across the river, that is state 1, and the goose is across the river, state 1, and the beans are across the river, we win. For either side, if the fox and the goose are there and the farmer's not there, it's unsafe, aka bad, don't go there. And then the same with the goose and the beans. So if the goose and the beans don't have the farmer with them, that's not a good position to be in. We can also say that the state has to be legal. There can't be 2 farmers. We can't have 2 farmers. There can't be 2 geese. No duplicates, okay? Which is easy to do when you represent things as sets. Then we have game logic. And the game logic isn't too bad. The game logic is we copy the state, we get our current side and the opposite side. We make sure that the state is legal. If it's illegal, we return illegal. We check to see if the farmer is on the one state. We set that right. If the farmer's on the other state, we set it right. If the farmer isn't in any state, why are we here? It's illegal. And if the thing that we're moving is none, or we're not in the current, and it's not current, it's not none and it's not current, we return. And then we do the move. So we remove it and we add it to the opposite side, and we remove the farmer and we add the farmer to the opposite side. Then we evaluate the state and return. Evaluate state, remember, was do we win, or are we unsafe, or are we safe? Okay? So now remember, I wanted all paths. So I'm going to use product in this case. Combination isn't going to work. So I've made this little helper called evaluate moves, where I give it a list of moves and a start state. And then it basically checks to see if when we move, did we win or are we safe? If not, false. And if we're out of moves, we don't win either. So let's do some unit tests. Evaluate the moves. Beans. That's all of our moves. Okay, we move the beans. What happens? Who gets eaten? Goose is eaten. Bad. Okay, move fox. What happens? Okay, goose gets the beans. Okay, so here's where I move the goose, and then I don't do anything. I move the fox. Then I take the goose back so he doesn't eat I take the goose back so the fox doesn't eat him. And then I leave the goose and I take the beans. But I haven't got to the other side yet, so I didn't win. The farmer just sits there and does nothing with some beans and some fox, whatever. So that's not win. Now, I do have a win state, which is goose, none, fox, goose, beans, none, goose, which is a lot of silly movement. You should probably just get a cage or something and get a bigger boat. It's kind of dumb. Anyways. How many solutions exist for n moves? For I in range, move 1 move to 11 moves, print the number of moves, and then get the product of that many moves from the moves I can make. So I can move a goose, a fox, a beans, or a none, right? Like I could have left the goose on the other side and I didn't want to take him back, so I just rode across.
Why are you choosing 11?
Because 12 is big. Yeah, you can choose 12 in your own time, but 300 seconds later, you'll figure out that 12 was a bad idea because it's an even number of moves and it's not going to work out. So then you try 13, and then maybe you have more than 5 minutes of wait time. And then you figure out maybe I should give up at this point. We'll get into that in a sec. All right, so move the beans, false, 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 good. Make the actual winning move, good. So how many solutions exist at n moves? So 1 has 0 moves, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7 has 2. So I think this is the one that we tested, but you can actually take the beans instead of the fox. So you actually have a choice here, and then that choice propagates there, but the end and the start are all the same. So you got 2 winning paths at 7. Do you have any winning paths at 8? No. You don't. You could have won, but then you left in your boat, and then the goose was eating the beans and got eaten by the fox. So yeah, you don't have any safe states at 8. At 9, though, you could just really muck around with that goose. Like, the goose is in the boat, and then you get serious about it. Right? And there's lots of these different, like, fooling around in the boat kind of deals. Sometimes they repeat over there. And then, you know, we get to 10, and there's not much going on at 10 because it's even. We hit a winning state, and we didn't. We rode into the middle of the road across, and the goose ate the beans again. Okay, so that's kind of cool. So we know we got 2. I didn't actually realize there was 2 winning solutions at 7. I didn't think about that. I knew one way, I didn't know the other way. I was surprised by that. I hadn't thought about the game that much, but it was kind of neat. And then at 9, it's obvious that there's no sense going any further because it's really just rowing around with a goose in your boat.
So, is there a reason why you chose 11? Like, is it trial and error? You try like one iteration and then you just keep going up? And
Yeah.
you actually find a solution?
That's part of it.
7 is the actual solution, but when you put the range in, do you guess and just trial and error at first?
Yeah, let's go 14 here. 9, good. 10 took a while. This is why I didn't increment it that much for a talk, because it is working right now. It has not terminated. There are a lot of, 11 came back, good. And for 11, we can see that there's a lot of mucking around. And I don't think it's done 11 yet. Oh, it's still working. Oh, it's now changed and made it hard to present. That was nice of you. Okay, still working on 11. Okay. This is the reason why I didn't have anything above there. Like, this is going to run for a while, and my state representation is garbage.
So would you know which number to start at? Or is it just trial and error that you start at 1?
I started low because I knew that small numbers have small factorial values. Yeah, and I knew from prior stuff that, you know, like 2 to the 14 is already pretty big, right? Like, that's 4,000, so that's 4,000 combos, and then you start incrementing that more, it goes pretty nuts. So what I was dealing with here is I had about 4 bits. So that's 2 to the 2, so 2 to 11, 2 to the 22, that's like 4 million, right? So it blows up really quick, and Python's only so fast. Like, Python's not the fastest language. This would be better done in something a little closer to the middle. And my state representation, again, total garbage. Like, you really should just do this as a graph and enumerate those states. And there's not a lot of states. Yeah, like Ryan's stuff is like way better.
Yeah, you can do this as a tree fairly simply.
Yeah.
It's a cool way of thinking about it.
Mm-hmm. So that was product, and if you want to do like all GCC flags, that'd be combo. If you wanted to do like different Photoshop filters in a row, that would probably be permutation for most of the filters. So it's a good way to think about it. You can use these things to solve all your problems that are related to sets and permutation combinations. And if you get really stuck, you can go read the Art of Computer Programming, which some of the drafts are available for free. And they're actually very good. Like, they're full of really neat things in permutations. Like, what he's describing here is the church bell ringer's problem. You got 5 church bells, and you're stuck ringing church bells for an hour because that's what you're told to do. So what are you going to do? You're going to try to go through all combinations, all orders of the church bells, because you're bored stuck up there in the tower hammering those bells. And so there's like different orders you can take, you know. It's pretty neat. So I really recommend browsing through it. And, you know, there's lots of exercises if you really want to work at it. But his description of the algorithms is pretty concise, not super Pythonic, but whatever. He's not too into Python. All right, so any questions about permutations, combinations, products? All right, I'll start handing out the quiz. All right, cool. Thanks for your time.
Thank you.